So suppose you go to a restaurant and order your meal to a waiter, but it turns out for some reason that waiter is the only waiter available there at that time. So what happens when a lot more people come in and order meal from the same waiter? It would delay our food, their food, and in case if the waiter feels sick, everyone's order will get really delayed and it can cause a very negative impression on the customers. So as we discussed in previous slide, we can easily solve it with horizontal scaling. In this case, it being hiring more waiters. Now, while we have solved the problem of less waiters, there's another problem we need to solve. What if despite having four waiters, somehow the customers are still giving orders to the same waiter? So despite having more waiters, now the same waiter is getting overloaded with orders. So how do we solve this? What we need to do is distribute the orders to different waiters evenly. This is what we call load balancing. The load here being the customer orders. One way of doing this could be to assign a table number to each table and have dedicated waiter assigned to that table. So there are different algorithms of how a load balancer works. Now mapping this to our system design, if all the requests are being served from the same server, then it would get overloaded and exhaust all its resources like RAM, CPU and storage. When this happens, there is a high chance that the server will go down altogether. So what load balancing means for our system is distributing these requests to all the servers in a feasible manner. The role of this load balancer in the middle is to keep this information abstract from the client, as in the client does not need to care about which server it should send the request to. That's the job of load balancer itself. There are different softwares in the market you can use to implement load balancing. Two such softwares being HAProxy and Nginx. Let's look at some of the common use cases of load balancers. A load balancer can prevent overloading of resources. It can prevent requests from going to unhealthy servers. And since load balancer will be distributing requests to many servers, a single point of failure will not be there. Now, there are a lot of algorithms which different load balancers use, the most common being round-robin load balancing. In this, the load balancer cycles through all the servers to find the first one which can serve the request, and as soon as it finds that, it sends the request to that server. Now, what do we mean by the first server which can serve the request? This could be any metric really. So this means that the load balancer forwards the request to the same server until the server can no longer serve any more requests. This approach focuses on fairly distributing rather than equally distributing. This is quite a simple yet effective approach. So if you're just starting with developing a new product, this approach might be suitable to you. You can find more resources attached to this slide if you want to read about other load balancing strategies as well. Now, like anything in the world, a load balancer isn't without its problems. The load balancer can become a performance bottleneck if it does not have enough resources or if it is not configured properly. Since a load balancer is now extra layer between our services, it increases some latency, although in most cases this latency is quite acceptable. Introducing a load balancer to help eliminate a single point of failure results in increased complexity of the system, so a very small simple app may not even require load balancing. A single load balancer is a single point of failure. Configuring multiple load balancers further increases complexity of the system. So these are some of the points you need to consider while deciding whether your application even needs a load balancer or not.